Okay, welcome everybody to this new webinar of the series organized by the IFAC Technical Committee on Control Education. I'm very happy to introduce Anthony Rossiter from the University of Sheffield in the UK. He's a very well-known researcher in the control community, and well, let me say, most of all, he's also well known for his activity in control education. He was the chair of the technical committee before me. Okay, so I'm very happy to introduce him. He will talk about a custom MATLAB toolbox for teaching control 101. So Anthony, the stage is yours. At the end of these 45 minutes, I guess, you can raise your hand to make any question, and they will allow you to talk. Anthony, please, and thank you for being here.
Okay, thank you, Antonio. So I apologize if some people have heard this talk before, but I guess reinforcement always helps and gives you more chance to think of and ask questions and interact. So, oh, that didn't work. Let's try again. There we go. So, just to remind you of the context then. So the context of this talk is an introduction to control, or basically a first course in control. And why are we talking about this toolbox? Well, the first thing is we want students to focus on understanding core concepts. And you probably all have the same conversation. Certainly, I was talking to my colleagues this morning, and we have problems that modern students seem to be really keen to learn by memorization. They want to memorize these things and regurgitate them, and without actually understanding what's going on. And clearly that is not what we want. We want people to understand what's going on, to understand the feedback, understand what is feedback, why is feedback important, and so on. Now, one of the problems is that typical feedback problems tend to involve lots of tedious numerical computations, and that can be a distraction because students then start thinking the course in control is about mathematics and about number crunching. And again, that's not really what we want. We want them to focus on what is control. Why is it important? So we want to sidestep the tedious numerical computations. So what's the underlying philosophy? We're going to use MATLAB to do all the number crunching. Because we take the basic assumption, number crunching is something they've done at school. They should be able to add, they should be able to multiply, they should be able to do simple things. I'm not giving you marks for doing number crunching. It's, you're at university now. You don't deserve marks for stuff like that. Let's give students marks for understanding, for demonstrating they know what they're doing. And so any number crunching, we give them MATLAB. Now, obviously, you may have a different tool, but today we're talking about the MATLAB toolbox. So if you want to find the resources, okay, basically you go to MATLAB and you go to the add-ons. Now I'll show you that live because that's the easiest way to do it. So if I bring in here a MATLAB window, okay, so let's just go to home. So if you look, hopefully you can see the mouse. You'll see there's this button which says add-ons. You simply select get add-ons, and it's opened a different window, which is massive. So sorry about that. Go in this different window, type control 101. Okay, it should appear. All right, there you go. It's appeared. And then you should be able to basically add it. Now, the problem, I've already got it installed, so it might not like me, but it's as simple as that. Okay, so if you want the toolbox, just go to the add-ons and download it, and it's free. You'll find it's also on GitHub. It's also on MathWorks File Exchange, and on my website, you'll see it's got a lot more information about it. So I'll just show you that briefly. So there's my web page, and you'll see it's got a lot of information about the toolbox and so forth. So information's easy to find if you need it. Okay, so this is just to remind you how to get it. You go to the add-ons, search for Control 101. Okay, and when you've done that, it will automatically populate. So again, if I bring this MATLAB window back just to show, if I go to this apps tab, you can see here a lot of the apps which come with the toolbox have automatically downloaded here at the top. So they're very visible, very easy to find and to use. Okay. So what I want to do next is give a quick summary of what we've produced so far. And there are some videos on YouTube basically giving a quick whistle-stop tour, if you like, of how to use some of these resources so you can decide how you might embed them into teaching. And you'll notice I put at the bottom that a new topic that we're working on at the moment is state space. So if you want a compact list and summary of the current files, now actually I'm going to tell you this is causing problems. This command here, .control 101 toolbox. But again, I'll demonstrate the point. So if I go here and I put that command in, there is .control 101 toolbox and press return, then it opens this window here. Okay, now the point about this window is it has soft links to all the files. So instead of having to remember, the file names are all quite long. Instead of having to remember the file names, you can just go to one of these soft links, press it. So for example, there's a really long one. That's one of the ones we're working on for state space. I can just press that link. And if I show you, there it is, it's opened it in the corresponding editor. Okay, I'll bring it back later. So that makes it a lot easier for students. They don't have to remember all these long file names. They just press this doc and then they get this other window and it basically gives you a summary of what the file does and a soft link to open it. So that should make life a lot easier. You can also do help. Let's find, is it up? Oh, I've not done it. We'll try it. Hopefully this will work. Help control 101. All right, that's what happens sometimes, depending on where you are. There you go. And you can see these are also soft links, but it's a lot briefer and it's in the command window, so it's not as convenient. But again, you can press any one of these links and the files will just open. So what it means is you don't have to remember the file name, type the file name. It makes it a lot easier for students once they get used to it. Okay, so what sort of files have we got in the toolbox? So we've got virtual laboratories. So these are interactive GUIs that users enter their choices through buttons, drop-down sliders, and so on. The code is all hidden, and there's a limited number of things that students can choose, but each of these come with a manual. And when you run the GUI, the manual is opened automatically, and that gives you all the technical background, and I'll show you one of those briefly. Okay, there are live script files. These focus a lot more on the technical detail and the MATLAB coding that you might use. So these are intended to give student frameworks that they can use for independent studies. So if they have a coursework that requires them to put in a specific example, specific tuning to produce specific plots, then the live script files give them templates. How do I do this? How do I do that? Okay, so they have a starting point. They don't have to create the code from scratch. Okay, and finally, a work in progress at the moment is we're starting to look at Simulink files because they enable you to look at nonlinearity and other things which are not so easy with just MATLAB. Okay, so first then, a quick illustration of some of the apps or the GUIs. So if you go to the website, you'll see it gives you a rundown of what virtual labs, if you want to call them virtual labs, apps are available. You can see a sort of a screen dump of what they look like and a short paragraph explaining what's there. So if you want to see a holistic of what are all the apps that are available, best thing to do is just go to the website and have a look. And I will just demonstrate a few. Okay. So manual first before we demonstrate. So whenever you basically run a file, run one of these apps, then the manual will open automatically. So here's an example of a manual that goes with one of the tank leveling apps. And you can see it's written to have a lot of text and a lot of explanation, and you can see it's written with equations. What's the mathematics and the modeling that goes on beneath this? So the whole point of the manual is to give a bit of background as to what's going on in the system. So whenever you run the app, these manuals open automatically. The other thing you might want to notice, sorry if it's a bit small on your screens, you'll see when they open, what happens is a copy is opened. You'll see here this file's got the name my copy. So it opens the manual in the student's own area and with a file name mine copy. And the idea is that the student then has their own personalized copy forever and they can edit it because there's lots of code snippets in the manuals. So students can then edit those and use them if they want. I'm sorry, I'm in the wrong window there. Okay. So let's look at some of the apps. I'm going to bring them in just to show the point. So here's the first app. This is car simulation. So you can choose your parameters. All right, you'll see there's 5 sliders, and when I'm ready, I can press simulate and it will run. Okay, so you can see the car is moving. Okay, and you'll see there's a plot of the response. Now I can do things like change the mass and simulate again. And you'll see the legend down in the bottom is keeping a record of what changes I've made. So I can change the mass again, run again. And so what it enables the student to do is do sort of systematic studies of what happens if I change this? What happens if I change that? So I can change the road slope. So it's now going to go uphill. What happens now? So what was the impact of the slope of the road on the behavior? Is that the impact you expected? I can add some wind. Let's simulate again. What's happened? Was that the impact you expected? So hopefully you get the point that the idea of these apps is to encourage students to think conceptually. What do I expect to happen if I change this? What do I expect to happen if I change that? And to carry out some systematic studies. Now, you'll see the window's beginning to get a bit busy, so you just press the refresh button and you can start again. If you get fed up with the animation, switch the animation off, and now I can do a simulation. That's with a wind of 10. Let's do a wind of 15. Let's do a wind of 20. And you can see once you've had enough of the animation, you can see what's going on. You can actually generate these comparisons very, very quickly. And hopefully you get the point. The idea is to encourage the students to think conceptually, to ask what if questions, and hopefully reinforce their understanding. So that's the car one. So I'm just going to demonstrate a few. There are lots, and obviously this next one is to encourage students to think about first order behavior. So I need to find a first order model that matches this step response. So my job is to guess what's the time constant and what's the gain. So it's put some values here. I'm just going to check them. They might be rubbish. So what can you see? Well, with my guess of 4 and 5, the gain is clearly too small. Not sure about the time constant. Let's try and get the gain right. Let's try 8. Check again. Well, it's a bit better. It's still a bit low. Let's try 10. Bit big. Let's try 9. And hopefully I'm deliberately not being too clever. And you see the point that the students can iterate to getting the gain right. And now they've got to look and try and get the time constant. Well, let's try something like 7. Okay. And you can see now it overlaps. So the student has got the correct time constant and the correct gain. And again, yes, you can do this iteratively, but the idea is to encourage students to think about how do I actually get these right first time? So now do a new random example. Try again. What do I think the gain is this time? Well, I'm a bit brighter this time. I think the gain's going to be about 4 and the time constant's going to be about, I'll put 1. I might be right. I'm just doing this quickly. And yeah, you can see I've got it right first time. So this is the purpose, that the students can play new examples. They can keep creating new examples as often as they like, practice until, yeah, I understand what's going on now. I've got the concepts. I can move to the next topic. So let's do another one. So this next one is an example of what I call a storyline app. So it does a sort of a whole design process from the beginning to the end. So at the moment, we're on the first tab, which is open loop behavior. So I want to understand, how do tanks behave? So let's press simulate. And you'll see it's a bit like the car one. It produces some plots. It's a little bit slow, this animation. I'll switch the animation off in a minute to make it quicker. And you can see what's happened here. If you look in this bottom right, it's introduced a disturbance flow and a blockage. So the blockage you can see is here, it's blocked the outlet pipe a bit. It's also introduced an extra disturbance flow, and you can see how the behavior has changed. Okay, so now you might want to say, well, what will happen if I make the blockage a bit bigger? Let's make it 60. I'll switch the animation off and run again. And now you can see you've got slightly different behavior. What if the blockage is slightly bigger? And run again. Okay, so exactly as before, the idea is that students can explore. What happens if I change this? What happens if I change that? Can I get an understanding of how tanks behave? Now, once I've done that, it's clear everything, I move to modeling. So the next tab is I want to try and model this system. So let's do a simulation. Okay, there's the plots on the right, and you can see this bottom left plot actually gives you the correct time constant and gain. All right, it basically saving you the effort of guessing, because this is a storyline one we don't want to take too long. So I've now got a time constant and gain. Now, next tab is manual control. So the idea of this is to get the students to try, okay, and control the depth in the tank by manually setting the flow. So I'm going to include disturbances, blockages, and so forth. So I'm going to start the simulation, and now I'm going to increase. You can see as I move this slider, it changes the flow. And what I've got to do is try and get the flow right to get the level right. Okay, now I'm not doing a particularly good job. It's not too bad, but hopefully you can see what's going on. That I'm basically moving it with my mouse. Now, if you look in this bottom right-hand curve, what you will see is disturbances and blockages keep changing. And as a consequence, I've got to keep changing this to keep changing the flow to reject the disturbances and the blockages. And the idea is the students will realize this is quite tedious. They'll say, yeah, I can do it, but I'm getting a bit fed up. You know, things keep changing. The real world keeps changing. I keep having to move the mouse. I can do it for a minute, but I'm going to start getting bored. Okay, so it gives them a motivation to move on to PI design. And now the idea is choose some PI parameters based on, you did your modeling back here. So you've got your time constant and your gain for your system. Use those parameters, do a systematic PI design. So I've just put I should have refreshed first, sorry. Refresh. Is that a good PI or not? Doesn't really matter. I haven't tried to tune it, but the idea is the students can now do some systematic tuning and try and get a decent PI. So I'm just doing it randomly here. And once they've done that, they can then evaluate their control in a more realistic scenario. So you can see here I've got blockages, measurement noise, measurement delay, disturbances, and this one will just run. And basically all that happens is that periodically you will get changes. You'll get changes in the blockage, changes in the measurement noise, changes in the measurement delay, changes in the disturbances. And what you're trying to do is evaluate how well is my PI working. Okay, you can see probably up here not only the noise but the measurement delay. Okay, you can see the red signal is delayed behind the blue signal. So enough. I can stop that. And I'll show one last one. I don't know if I'm taking too long here, but I think we've got plenty of time. So this one is proportional design with a phase margin. And again, the idea is to try and hide all of the detailed number crunching and get students to focus on concepts. So what's the concept? If you look in this middle plot, you'll see I've got the current phase margin marked in this pink sort of vertical line. So that's the current phase margin. And then you'll see on the left, I've got the target phase margin in this green color, which is this horizontal green line going across here. So my target is to try and get the phase margin basically to be marked by that green line. Now, what I can do is just try and change the gain K. So here I've got a slider, change the gain K, and what you'll see is the pink line has moved. So I can keep changing the K, and now you notice I've got the pink line basically to intercept the green line on my phase diagram. So I've now got the phase margin to be roughly what I want. Now these sliders only allow crude movements. You're not going to get decimal places. But the idea is to allow students to engage with, very, very simply, what's going on. Okay, how do I do a proportional design? What is it I'm trying to achieve? Now, they can use buttons at the top here, like overlay several KP. So you'll see these gain plots show you how the gain plot changes for different values of KP, and under it, how the phase margin changes for different KP. So the colors all match. And then under that, the corresponding closed loop responses. So I'm going to say, I want the KP to be roughly this green color. So which one's this green color? Go to the legend. That tells me KP needs to be about 1. So let's set KP to be about 1. And indeed, I've got roughly the right phase margin and so on. So hopefully you get the point. Students will need a little bit of nurturing to use the apps, but the idea is, as hopefully you've seen, focus on the concepts instead of the number crunching. Get them to understand the key steps. What is it you're trying to do? And the number crunching can come later. Okay, so there's many apps. I'm not going to go through any more at the moment. Hopefully you've got the message, and basically what we've done is illustrated the potential, and you see the point. Remove the need for tedious number crunching so you can focus on concept. And there's quite a lot of files which hopefully cover most of what you want in a Control 101 course. But if there's gaps, talk to me, help me fill the gaps. We can put them in the toolbox very easily. I think hopefully Katerina's working on one at the moment, which we'll be able to put in quite soon. So live scripts. So we can't avoid the number crunching altogether. At some point, the students need to do the number crunching, and that's what the live scripts are for. So you can see we've got a large number of live script files, which basically go through a control course roughly in the order that would be typical. Start with plotting, because if you can't plot, then you can't illustrate anything. Then how do we solve ODEs? Then look at behaviors of first order models, behaviors of second order models, introduce Laplace transforms because it's a useful tool. So 7 and 8 are about Laplace transforms. Then we start looking at transfer functions and poles. And then we start looking at behaviors, generic behaviors, step responses with MATLAB, and then we move on to feedback at the bottom. So you can see there's a fairly logical sequencing of these files. So what do these files do? So what we're going to do is break down a first course into the different concepts and then the mathematics required to support this, and then what MATLAB code will do that number crunching for you so that you can use MATLAB to do the tedious side and you can focus on the more interesting intelligent side. Now, the advantage of using live scripts is that students can change the numbers in those live scripts, and so they can self-test their understanding. So I'll give you a brief illustration of what live scripts are and why we're going to use them. So the key thing is you can see live scripts have got explanation on the left and the results on the right. So it allows students to basically say, oh, change this number, press go, and the new results appear on the right. So they can see side by side a neat presentation of the theory, the code, and the results. So it's nice and compact and hopefully makes it very easy for students to experiment. So here's an example. You can see illustrating BODMAS rules. Now this is a silly example just to demonstrate the point. So the students have done this calculation, F equals A plus B times C over B plus C, and you can see the answer has appeared here on the right. The students can change those numbers and then press run section and it will reappear. So I'll move on to some more interesting examples and demonstrate later. So solving first order ODEs. You can see here on the left, we've got the explanation, nice and neat. What's a generic ODE? Which ODE am I going to look at? And then the MATLAB code for solving this ODE. You'll see the 6 has gone down here, the 4 has gone here, Oh, sorry, I've changed that 3 to a 7. That's naughty, bad slide. And the 2's gone there. And then the result over here. Now, let me just find that file. So that file is called ODEs with MATLAB. So I'm just going to open it for you, bring it across. Here it is. Okay. And so there's this example with the error that should have been 3. But anyway, so I changed that to 3. You can see I've just done that real time. Press run section, and you see the result updates on the right hand side. The student can say it wasn't 6, it was actually 8. Change the 8, press run section, the result appears on the right hand side. So what you're doing is you're giving students the code they need to solve the typical problems so that later on they can put in their own numbers and solve their own problems. And so now they're not having to do the detailed number crunching. They can focus on understanding what's going on. Okay, I'll move that back out of the way. So you can see here explanation and notes on the left, code snippet in this sort of shaded grey box, and results on the right. This is a different example. It's also from the ODEs, but it's showing what if I want to create a plot. So you can see it's showing once you've got the solution, which comes out as a sort of symbolic value. There it is. So it's symbolic. It's got this function of t. Then how do I evaluate that and turn it into a number? So it's given them the code there, and then I can do a plot. So again, the same structure as before. Okay, what about modeling? So this looks at first order modeling, this next one. And you can see here, the students can put in some guesses for what the time constants and the gain are, press run section, and it will update this plot on the right-hand side. Okay, understanding underdamped systems. Different one again, you see the same sort of pattern. Closed loop transfer functions. So you may want students to generate closed loop transfer functions. Again, you see the explanation here. What are the closed loop transfer functions? And then down here, what's the code which will generate those closed loop transfer functions for you? And over here on the right, here are some answers for the numbers you put in up here. So hopefully you'll see the point. These live scripts are very, very useful because it allows the students to relate their theory, which is explained in the left-hand side of the window, and then what MATLAB code will do the number crunching for me, so I'm not having to waste time doing lots of complicated number crunching. I mean, certainly with these closed loop transfer functions, once you get to second, third, fourth order, it's really tedious on pen and paper. Let MATLAB do it for you. Okay, so that's a different example, proportional design with Bode, but there are many. Okay, so this example, lead compensator design with Bode. So again, you see now the explanation in the left-hand side is getting a lot more involved. The code I've hidden from this particular slide, but you'll see here's a plot on the right-hand side illustrating what you're trying to achieve. Okay, so the idea is the students can change the numbers and the plots will update. So hopefully they get to understand the concepts. They can see, oh, I've changed that, and this is what's happened. Okay, so this is just to highlight state space systems. This is work in progress. So here's a list of some of the files that we're currently working on. Again, a sort of logical path through a module that would focus on state space systems, state space behaviors. Hopefully this will be ready in about a month, and then we'll add it to the toolbox. Okay, so are there any of the others? No. So I've illustrated again fairly quickly the potential of LiveScript files as useful resources to support independent learning and trial and error learning. So encouraging students to say, I think I know what's going on. What if I change this number? Has it done what I expected? Critically, again, you'll see removing the number crunching. So we're using MATLAB here to do the number crunching so students can focus on the core concepts of control, behaviors, and the role of feedback. And hopefully we've got a good breadth and cohesion of files which will cover most things that you want. If there are gaps, let me know. Help me fill the gaps. I'm quite relaxed about this. Okay, so my experience is the students really like the LiveScript files, and they have been used very actively by students, during tutorial sessions certainly, and for learning the basic concepts. So Simulink next. So this is sort of work in progress, but we've begun to make a start. So Simulink is an important tool for capturing the models of real systems. So the fact that you can do block diagrams, use lines to represent interconnections and things, you can capture nonlinear behaviors. It's a lot easier to build models for real systems than perhaps if you just have MATLAB and you've got to write code. Okay. However, my personal viewpoint is I much prefer MATLAB as a tool for handling data definition, for doing plotting, parameters, etc., etc. So what I would tend to do is create the Simulink file for the model, but use MATLAB to run the Simulink file, because that makes the overall process a lot easier. And I'll illustrate that. So what we're trying to do is immunize students from too much coding and focus on the use of Simulink files to get a better understanding of dynamics and control. So I've used LiveScript again. So perhaps if I show you an example, that will probably be easier. So if we bring this in, I can close that one. We don't need that anymore. Can close that. We don't need that. Close that. Right. So let's look at this one. Oh no, wrong car. It's this one, car suspension. So this LiveScript is actually about Simulink. You can see in the title, using Simulink. Okay, so if we go down, you'll notice again, as before, we've got the explanation. What's the engineering background that we're looking at here? So here's the model that we're talking about, a schematic of a car suspension. And here is the Simulink file. Okay, so this is just a screen capture of the Simulink file. It's a very simple one, and it's only using transfer function blocks, but we've got more complicated ones coming. And what you'll notice is we import data from MATLAB. Here's the block which is importing things from the workspace, and we export things back to the workspace here. So that's a deliberate choice, because I want to run this file not by opening Simulink and pressing the run button and using scopes, because that's a bit messy. I want to be able to make everything transparent. So you'll see here, I've got this code snippet where all of the data is defined. And the advantage of that is if you want to change the mass, you want to change the spring, you want to change the ground profile, you can just look here and you can say, oh, the mass wasn't 500, it was 550. So just change it, just like that. Press run section. Okay, don't worry about that warning. That's basically linked to, I'll explain in a minute. But anyway, it's updated the figures for me. So what you're trying to do is immunize the students from too much stuff that you don't want them to worry about, and run the simulation using MATLAB code. Okay, and then handle the plotting down here. So you'll see the simulation is just this one line here. And the rest of it is I'm defining the data that my simulation needs. Okay, so that's one example. I'll press no. Okay, so we've got a different one here, and this is basically part of the draft that we're doing for the state space section. So if you want to start using observers and feedback and other stuff, it starts getting a bit complicated with MATLAB code when you're doing state space. So what we've got here is a Simulink model, which has got the state feedback, and it's got the observer. So you can see the observers down here. We've got integral action in here, and where's the state feedback? Oh, there's the state feedback down there. So we've got the state feedback, we've got a feed forward, we've got an observer, and basically Simulink is a logical tool for basically putting this together. So we're including that in the sort of files that we're generating for the state space. And again, you'll see we've got the MATLAB code here to enter your system. So rather than students having to do it elsewhere, they just do the code snippet here. Here's your model. Here's how I build my observer. Okay, so all the steps with code snippets, nice and clear. So the students can see all the design steps, everything that's going on. Input signal characterization here. and then the simulation and the plotting. Okay, so enough on that. So key point here is the Simulink files do not need to be touched, but if you want them, you can open them and change them. Okay, but the files that are written for the toolbox assume that you're not going to change the Simulink files. They will just run. Okay, but you can copy them, and you can copy the LiveScript files and make edits for yourself. Okay, so that's an example of the car suspension, which I've just shown you. And this is an example of a position control one, where you can see we're looking at nonlinearities. We've got backlash, we've got rate limits, we've got saturation, and so on. So the idea is that the students can now explore what happens if I get these nonlinear, oops, sorry, that's gone the wrong way, these nonlinear components in my control loop. And they can switch the nonlinear components on and off. So with these buttons, green means include, red means don't include. So a toolbox summary. Yes, I've got plenty of time, haven't I? So we've got a large suite of live scripts, virtual laboratory, Simulink files, and MATLAB code. And basically what it comes down to is how do you want to use these? And why have we done it? Because we want students to focus on understanding. How do I expect behavior to change if I change this value? What happens if I introduce this nonlinearity? What happens if I increase the mass? What happens if the feedback gain goes from 3 to 4? Okay, if you had to do that on pen and paper, it would be really tedious. It would take ages, and the students would be so bored and distracted by trying to do number crunching on pen and paper that they would lose sight of what it was they were trying to do, which is manage the behavior of a system in the face of real life uncertainty. Okay, now obviously to use these files, you need to curate them into your module, into your course. And obviously that's what I do. There's a wide range of files. You might not need them all. You might only need 3 of them, but you need to basically curate them and show students this week, I want you to use this file. This is how I want you to use it. This is what I want you to learn. Okay. So pretty much that's at the end. This is just to emphasize, okay, I've done so much. I'm not expecting it to be perfect. I'm not expecting it to be complete. We're interested in other people contributing to this toolbox. You might say, well, I like what you've done, but you've missed, this is a really important topic which we cover in our university. Can you add that in? And my answer is going to be yes. You help me write it, we'll put it in. It's as simple as that. Okay, so you help me write it, we will put it in. What we want is this toolbox to be something useful to the whole community, something that you can all use. So you don't have to use the whole toolbox. You pick the bits that are useful for you, for your scenario, your university. And you might want more apps, or you might want more live scripts, or you might want more Simulink, or even something else. If you want help developing things, I'm quite happy to help. There's lots of templates available on my website. So if I just quickly bring that back and show, if you want some of the source files, just go to my website. You can see where it says Google folder. I won't say they're all in there, but if you click on that Google folder, then what you'll find, a lot of the source code is there. So if you want the source code, the templates, so you're not reinventing the wheel, if you want to talk to me for half an hour with a Google Meet and say, how do we do stuff? Easy to arrange. Okay. And I think the rest of these slides probably we don't need to dwell on now. I think I should stop there, Antonio, and give time for questions.
Thank you very much.
And what I'll do is I'll move my camera so I'm looking at everybody rather